Okay, so the first thing we're going to talk about today are S block elements. Remember, we talked about how you can look at the periodic table as different elements or different families or different periods, which are all very good ways of looking at the periodic table, or we can look at them as blocks. And so today we're going to talk about the different periodic blocks. So the first block we're going to talk about are the S block elements. And S block elements have some unique relationships. The first thing they have are diagonal relationships. Yesterday we were talking about relationships in families, how families have similar trends in relationships. S block elements have some diagonal relationships so in addition to their horizontal and vertical trends, they have a diagonal relationship between such as lithium and magnesium, beryllium and aluminum, boron and silicon, where they have the adjacent upper left, lower right relative location on the periodic table. I'm going to show you what they look like in a minute. But basically, this says that elements within these diagonal relationships have closer properties to the element in the diagonal relationship than the next one in their own group. I'm going to show you what that means. So if we're looking at a periodic table, lithium is more closely related to magnesium in terms of properties and trends than lithium is to number 11. And I've pulled up a periodic table this morning for this very reason, and I've hidden it behind my computer. So just 1 second. Sodium. I was right, but I wanted to make sure. As in, sodium is more likely to be closer to calcium than it is to potassium, and potassium is more likely to be related to strontium than it is for rubidium. So we're going to look at S block as in hydrogen, because hydrogen is officially part of the S block. So is helium officially, but hydrogen isn't really part of the alkali metals or the alkaline earth metals, so we talk about hydrogen individually. And hydrogen is officially in group 1, that's the alkali metals, as it has 1 valence electrons, but it does not have any of the same properties of the alkali metals. In fact, it was discovered in 1766 by a man called Henry Cavendish. He called it flammable air because to him, it looked like air that was flammable. And a really cool fact is that universe contains more than 90% hydrogen by mass, meaning 90% of the mass in the universe is hydrogen. And the single valence electron is the reason of hydrogen's usual properties, because it has a set of both metallic and non-metallic properties. Hydrogen is a very unique element. Then we have the group 1, which is the alkali metals. The reason that they're called alkali metals is 2 different reasons. One, they react with water to form alkaline solutions. And the word alkali in and of itself comes from the Arabic word alkili, meaning ashes of the saltwort plant. They very easily lose their valence electrons. They always want to form a cation with a 1+ charge. They're very easily cut with a knife. They are found combined with other elements in nature. They're very good conductors of both heat and electricity. And when we start looking at electron configurations, they are S1. If you're wondering what the most important information to write down is or to study, I have bolded it for you. Although I can promise you the meanings of word is always a favorite of me to put onto tests. Then let's talk about group 2. These are the alkaline earth metals. Earths are from a really cool reason. If you know anything about medieval alchemy, which was basically medieval doctors, not quite doctors, like pharmacists, those who tried to heal, but maybe didn't know that much, they believed that a lot of disease was caused by an imbalance of your earth, air, fire, water. And that's what you had in your body. You had earth, air, fire, water. And if it was an imbalance, then you got sick. Therefore, almost everything that they looked at, they felt represented one of these elements. And because they could not burn them in their fires, they classified them as earths. Please do not ask me why it wasn't water. That would have made much more sense to me, but earths, I guess, didn't burn either. So they were our earths because they couldn't get burned. So alkaline earth is also reflective of two of the following properties. Alkaline, it forms an alkaline solution with water. And earth, it reacts with oxygen to form an oxide. It is less reactive than group 1. They're usually found with oxygen and other non-metals in the Earth's crust. They always lose 2 valence electrons with bonding, forming a 2+ cation. I'm going to put that, they form a 2+ cation. Their charge is 2+. Then when exposed to oxygen, alkaline earth metals form a thin oxide coating. And when we're looking at valence electron configurations, they are s2. And then if we're going to move forward, the big things we're going to talk about, column 1 is S1, and its charge is 1+. Column 2 is S2, and its charge is 2+. Those are very important things to know. We will be moving back and looking at this information in a different way in a couple of units and even in a couple of days, but getting that basic information down so you can either label a periodic table or start memorizing what things are is an important thing. I don't want to, I want you to see it multiple ways in different ways. And that is the S block. Okay, let's talk about the next group, which is the P block. Again, remember the S and P blocks are your representative elements. So groups 1 and 2 are S blocks. Groups 13, 14, 15, 16, 17, and 18 are your P block. So group 13, that's your boron group. It's important to know that boron is a metalloid. Aluminum, gallium, thallium, and yttrium, also known as niobium, are metals. They have 3 valence electrons, and they form a cation with a 3+ charge. Indium and thallium will act like transition metals with multiple oxidation states, meaning they can have different charges, and you'll have to be given those charges. Boron can also form a covalent compound. That is the exception to the octet rule. Let's talk about the carbon group. That is group 14. Remember, carbon is non-metal. Silicon and germanium are metalloids, 10 and letter metals. This is the group that, as much as we talk about families and groups being like elements that are similar in property, this is a group that is not true with. The only trend that really applies to the carbon group is that carbon is not representative of the other elements within the group. It's one of those groups that what holds them together is that they don't have any rules that really hold them together. They're all the little odd ducks. Here's some really important vocabulary when we're talking about elements and minerals. A mineral is an element or inorganic compound found in nature as solid crystals. An ore is a material in which a mineral can be removed at a reasonable cost. So you remove minerals from ore. And allotropes, this is really important. They're forms of an element in the same physical state, either solid, liquid, or gas, that have different structures and properties. I want you to think of carbon. You can think of like a carbon or a coal mine, that's carbon. Graphite from pencil, that's also carbon. And those clear diamonds, those are all carbon. That is all carbon in a solid because due to pressure and the creation of some different structures and properties, they look different, but they're all basically carbon. Let's talk about group 15. This is your nitrogen group. They have 5 valence electrons. They gain 3 electrons to form a 3 negative anion. An anion means that they are gaining electrons. There are metals, nonmetals, and metalloids also in group 15. So they have a wide variety of properties. Nitrogen and phosphorus are your nonmetals. Bismuth is your metal. Arsenic and antimony is your metalloid. And bismuth is just very confused. It wants to lose 3 electrons to form a cation with a 3+ charge. Bismuth doesn't like to follow the rules. Let's talk about group 16 now. This is the oxygen group, and it has 6 valence electrons. It has 2 nonmetal members, oxygen and sulfur. It has the metalloids, selenium and tellurium. It has the metal polonium. But all the elements primarily pretend that they're non-metals. It will take 2 electrons to form a 2 negative anion, and it can also share electrons to form a stable electron configuration. Then we have group 17. This is the halogen group. And they're named specifically for their ability to form a compound with almost all metals. And any compound made within a halogen group is called a salt. That does not mean that you can eat all the salts the halogen group forms. Most salts are toxic and poisonous. But remember, the word halogen means salt former. They differ in their physical properties. Iodine is a solid that changes directly into a vapor. Chlorine is a gas at room temperature. Bromine is a liquid, but it evaporates easily, but yet all of their chemical behavior is incredibly similar. They're incredibly reactive. They are always found combined with other elements in nature. The acetine is a total exception in here. It's completely radioactive. We have no known uses for it. It's just there to be there. They have 7 valence electrons and they form an anion with a 1 negative charge. And then you have group 18. These are your noble gases, and they're literally called noble gases because they're crazy non-reactive. They actually all float, and they kind of are above everybody because they already have their 8 electrons, so they are happy. They're very stable. If you really annoy them by giving them lots of energy, they'll form a bond or a compound, but they kind of do it unwillingly. There's no known compounds of helium, neon, or argon. They have 8 valence electrons, and we don't talk about the noble gases in forms of creating ions or bonds in this class. When we're looking at the properties of the p block elements, we have to also look at their numbers in terms of electron configurations. And also, it's nice to see, I'm going to put them right next to them, their charges. So column 13, it's P1, and it's a 3+ cation. Column 14 is P2, and we really don't talk about the charge of column 14 because it tends to only create, in general, either very specific charges of cations, which you are told, or it forms covalent bonds, which don't have charges. Column 15, as a rule, is P3 and has a 3 negative charge. Column 16, as a rule, is P4 and has a 2 negative charge. Column 17 is P5 and it has a 1 negative charge. Column 18 is P6. P6 does not have a charge because it is incredibly non-reactive. They are already happy with their 8 valence electrons, except for helium, it has an S2. Helium is not in the P block, it's still in the S block. And that are the end of our P block elements and talking about the representative metals or representative elements.